Okay, so let's now move to standard model physics at the lower end of energy ranges that we consider. Let's look at the interactions of particles with matter. This is in the context of detecting the particles in the different with different detection principles that we discuss in the following lectures. There are great books on this topic in general. One is Kolanowski and Vermes. Few of the chapters from this excellent book I follow in this lecture. It's highly recommended read. Now, we look at again at the Hadron Collider environment, and then we look at the interaction of the charged particles with matter. There's plenty to learn. There's little to calculate because many of the things cannot be calculated and can only be argued and can only appeal to your basic physics understanding, except the Bethe-Bloch equation, which we will derive, and that I think for a long time will be the last derivation that I actually carry out. Good, let's not talk about it, let's do it. We have discussed at length the environment at the Hadron Collider. Now, from the point of view of a detector, the problem is to solve, is to find a muon, for example, in a dense environment of the hadronized final states from initial state quarks, stop quarks, Higgs bosons, and whatnot. I think it's become clear that the typical final state can be very complicated because of the many processes that relate to strong interactions in a regime where it's non-perturbative. One more complication is that at the Hadron Collider, at all Hadron Colliders, to produce event rates of the interesting processes that are high enough that they can actually be detected, the instantaneous luminosity must be so high that in turn background collisions happen with a rate of 15 to 40 per bunch crossing. In 2016, the data we took in 2016, we had between 15 and 40 interactions in each bunch crossing. So not only do you have such a complicated event, you have 40 more digit events that I did not draw here because you couldn't see anything that need to be separated off first. We call this a pileup because it's a piling up of interactions in the same bunch crossing. It's not important to discuss pileup for the standard model physics we want to measure at the highest scale, but it's very important to discuss this when we talk about the detectors, because detectors need to sustain an extremely dense environment of particles from these up to 40 interactions. Good, so now a different view of the production of jets. We have discussed, I repeated a little bit from a different point of view. Proton-proton collision happens now in the lab frame. Two jets are ejected towards the center of the detector. We have our partons that we discussed this morning. Then we have the hadrons, where we have effective models for. The length scale of the parton interaction is 10 to the minus 18 meter, because this is the TeV scale. A GeV amounts to a Fermi, very roughly, the length scale of the proton, which is 10 to the minus 15. A TeV is therefore 10 to the minus 18. Hadron physics is at the proton length scale, 10 to the minus 15, but our detector is 15 orders of magnitude larger. Detectors are meter-scaled objects, centimeters to meters. In fact, it starts a few centimeters away from the beam pipe with hits in the tracking, then come electromagnetic calorimetry, hadronic calorimetry. And the particles we produce, we cannot distinguish for example, between kaons and lambdas, this is very hard. However, those particles therefore only leave hits in the tracker if they were charged, and then they leave deposits according to their energy in the calorimetry. And if we want to go backwards and try to learn something about the hard scatter, we have to reconstruct those jets and calibrate back our energy measurement to the initial parton momenta, and then start working on the standard model physics comparison. So the physical evolution goes upwards, the work of the physicist here goes downwards, and this is what we concern ourselves with for the rest of the lecture. Let me show you here to the right the simulated, because we can't measure it, but the simulated particle content of a hadronic jet. You see here on the x-axis the transverse momentum of the jet. These are die-jet collisions at the LHC. You have in colors the different hadrons and mesons. So you have pi plus, pi minus, kaons, sigmas, protons, and antiprotons. Protons and antiprotons are here these pinkish colors. They are created in roughly the same amount. A few more protons, because our initial state is 2 protons. So we have in our final state will be double positively charged. And then K long, K short, lambdas. And then we have a few photons. And then we have a lot of photons. Those photons that amount to roughly 20% of the jet momenta come from pi zeros, because a pi zero is a pion that instantaneously decays into a pair of photons. And then there's muons and electrons that can also be produced inside jets. That's a tiny fraction. You see that the average jet composition does not really depend on the jet momenta or the jet energy. It's really constant. It doesn't really matter whether we have a 30 GeV jet or a TeV jet. There's always a certain distribution of particles inside, and the average values at least do not change. However, average values don't tell you much about fluctuations. One jet can contain 60% photons and the next jet can contain 60% charged hadrons. That's completely normal, but the average values don't change. That's great, because we only need to know on average the interaction of the decay products with the detector as a function of the charge, the energy, the mass, and the lifetime. Lifetime we denote by tau. So charge, energy, momentum, mass, and lifetime these are the quantities that we parameterize our detector response with. That's really an enormous simplification. We don't have to reconstruct all those particles to infer the momentum of the initial parton, because it is known on average. Good. There are, of course, many known standard model particles that can occur inside a jet or can be produced in a proton-proton scattering. I put here a list of the baryon and meson summary tables. These are just deltas, lambdas, sigmas with different JPC, so angular momentum, parity, and charge. For most of these, we know very well their decay properties, so we can make accurate predictions. As we've said before, the difficulty is translating the low energetic quark and gluon fields into the hadron picture. Once you have hadrons, we know pretty accurately for most of the resonances how they decay. Now, we have now produced particles either in simulation or in reality. How can we detect them? Particles can be measured if they, point A, live long enough. If they decay instantly, you can only observe the decay products. Sounds obvious, but it is important. The majority of the particles are extremely short-lived. from the hundreds of particles, only very few have track lengths that are long enough that we measure them in the detector. One is the photon, it's stable. One is the proton, that's also stable. Then there is the neutron. Neutron is also stable. I mean, it lives 1,000 something seconds, so a quarter of an hour roughly, which is really stable when on the time scale we operate the detector, which is 25 nanoseconds. Electron is stable. The muon is also practically stable. At 1 GeV, it travels on average 6.1 kilometers before it decays. Its lifetime in its rest frame is 2 microseconds. Then we have pions, which can reach the detector. They can go on average 5 meters, and kaons a little bit more difficult, but 5 centimeters, a huge distance for vertex reconstructions, are k-shorts. So these are the particles that we reconstruct. We cannot differentiate between pions and kaons because for reasons that will become clear in this lecture. So you have here from this list an idea of the particles that reach they can traverse the whole detector. Now, is it as good as time as any to discuss the track length? The length a particle can travel before it decays is its speed times its lifetime in the laboratory frame. The speed, we write as c times beta relativistically, and the lifetime is gamma times tau zero, where tau zero is the lifetime of the particle at rest, or is measured by a clock that travels along with the particle. So we have a relativistic factor gamma here. The length of the track is c beta gamma tau. I think it's easy to remember. This is important because there are important particles with a small but finite lifetime, and these are the B-mesons, and we're very lucky that this is so. A B-meson has picosecond lifetimes. See the kaons, they travel with 90 picoseconds, 5 centimeters. P-mesons have picosecond lifetimes, which means we get the displacement of hundreds of microns. And if we get tens of microns resolution in the position measurement, we can identify B-mesons. Now let me tell you two things. First is the definition of the track impact parameter. Say you have a jet axis here, so this is the average momentum axis of a bundle of particles, and then you have a candidate track. The impact parameter is defined as the distance of closest approach. When we have a few hits in the tracker here, we may calculate a track because we know the magnetic field. Then we can compute the impact parameter by computing the distance of closest approach. And this displacement needs then be consistent with the lifetime of the particle. It's impossible or very unlikely to observe a displaced particle with a high impact parameter if its lifetime is very short. Can turn this argument around and say that it's very likely that we have observed a B-meson if we have displacements in the ballpark of tens to hundreds of microns. Now, why am I insisting on B-mesons? Because we got other displaced particles too. But B-mesons play a special role. The B-meson contains a B quark, and the B quark in the standard model is produced either via C2BB or top to BW, and it can also be produced strongly. However, the rate for that isn't, the background rate for that is not overwhelming. And the other cases where there's a p meson are extremely interesting. So C2BB and top to BW give us access to the third generation of fermions. So we use this impact parameter, this high impact parameter of track candidates inside a jet to tag whether that jet contained a p quark before hadronization or not. P quark gives you a p meson. P meson lives for picoseconds. Picoseconds mean hundreds of microns of displacement. And therefore, one of the few things we can tell about jets. Yeah, the jet is this complicated bundle, but one of the few things we can say with 70% with a 70% efficiency, whether this jet was a p jet. We can make this statement with an efficiency of 70%, and we only go wrong in about 1% of the cases. And that's quite excellent because we can use the presence of these displaced tracks to indicate whether a top quark was in the event. And top quarks are subject of intense scrutiny, and not a lot has been measured about the top quarks. So that was a long excursus, but I will insist on and keep talking about impact parameter resolution, because we need to measure this track distance with the best achievable precision. Now, we've talked about lifetimes now and how these are important. The other crucial ingredient that we can detect a particle is that it must interact with the detector. That is, it must deposit energy. Per unit length it travels through the detector material, it must leave a certain amount of its energy, the E over dx, and only once it's done that, we can transfer it into a detector signal. Neutrinos are a counterexample. Those interact only weakly. There, the E over dx is 0 for practical purposes. If you want to measure neutrinos, you need very large detector volumes. For example, the ice cube detector, which is several square kilometers of ice at the South Pole, that is instrumented with photodetectors. And the ice, you have cubed kilometers of ice acting as a sensitive material, or you need giant fluxes. And we have large fluxes at hadron machines, but these are many orders of magnitude away from the fluxes that the neutrino fluxes that occur close to the cores of nuclear reactors. Neutrino fluxes that are that close the measurements can be done with single crystals. If they are well shielded, they will record neutrino interactions despite the very low probability for an individual collision to happen. Okay, so A and B are necessary that we can detect a particle. Let's now make an overview of the interactions that can happen in the detector, and then we'll discuss them one by one next time. There are different types of interactions for charged and neutral particles, and charged and neutral particles also have different scales under quote for the processes that lead to their detection. Electromagnetic interactions can happen at the atomic scale because you can scatter and react with the electrons in the shell of the atoms. So we are talking angstrom. A neutral particle can at most, a neutral particle that's strongly interacting, so anything, a hadron, a meson, a baryon, is at the nuclear scale. We talk about Fermi, and for those strong interactions are the initial reaction that takes place when the particle hits the detector. Now, let's talk about the detection of charged particles. Charged particles can be identified by the ionization of the material along the track. If the charged particle is stopped or accelerated close to a nucleus, for example, an electron can do that, for example, it emits Bremsstrahlung. We already calculated that. That's completely analogous to the synchrotron radiation. It's just for an individual particle. Then there is Cherenkov radiation, which is emitted in case the speed of light in the material is lower than the speed of the particle in that material. You know that the speed of light in material is lower than the speed of light in the vacuum. In case the speed of the particle exceeds that limit, a shock wave of light is emitted called Cherenkov radiation. So that's charged particles. Photons can be measured by the photon and Compton effect, so interactions with the atomic shell. For highly energetic photons, the dominant detection process is pair production. Pair production of an E plus E minus pair by interactions with the very strong electromagnetic field close to the nucleus of a particle. We'll discuss the quantitative assessment of these processes in some detail. Now we have neutrons. Neutrons do not interact electromagnetically. Those interact only with the strong interactions. So you have to wait until a neutron hits a nucleus. Hence, if you want to if you want to measure neutrons, you should put a material with high atomic number in its path, with high mass number in its path. And then neutrinos, the weak interaction we already discussed, is very difficult. Either large detector volumes or high fluxes. Whatever happens, the neutrino will make one interaction, then will disappear, and you will record secondary particles. For example, an electron or a hadronic particle that it kicks out. And then you measure these and you're back to cases 1, 2, 3. Now in the following, we'll give a phenomenological treatment of the detector interactions with a focus on the implications for detector design. Now, what are important detector design criteria? Begin to view this from the other end. First of all, you want little interaction with the measured particle. For example, a charged muon traverses the detector, an electron. You want to measure its path, so you want to track its path. You do not want at each measurement to completely change its momentum because you lose the information of the initial momentum that it had. So you want to track a particle with as least possible interaction as possible. You want to do so with very high efficiency. That means if you have a particle, given a particle, you want to reconstruct it with the highest possible probability. You want high purity. If you have measured a set of, if you have measured a number of particles, you want to reduce, you want as low as possible a probability that some of these are only instrumental noise or some unintended signals. So, for example, a pion that is misidentified as an electron. In statistics, these two errors are typically called type 1 and type 2 errors. So high efficiency means that you do have a signal, but you miss it. High purity means you have a fake signal and you reject it. Both of these features are desirable and should be simultaneously optimized when constructing a detector. Typically, you measure one or more property. You measure the energy per particle. You measure, for example, the energy deposit, but you also know where your detector cell is located in space. and you measure when the particle has hit. So you want simultaneously high resolution in the spatial coordinates, so you want a highly granular detector with fast timing, with good energy resolution, and with good angular resolution. You want a fast signal processing because most of the signal processing has to be done with chips that sit on board of the detection module. And you want simple maintenance because you can't afford a crew of hundreds of people that keep repairing your detector and operate it. You also want simple detector control, and this should not be underestimated. At Hadron Colliders, at least, radiation hardness is a concern. If you can meet 1 to 6, then it's not worthwhile if if the beam close by completely fries your nice detector. So you need radiation hardness, and the collider conditions have to be known decades in advance for a suitable design. It's not possible that we operate the LHC at orders of magnitude above the design criteria, because it would just destroy the detectors that are close to the beam. And it should be cheap. Of course, this is all not possible. Everything is expensive. Well, 0.1 to 8 are a multidimensional optimization problem, and typically you can only pick 1 or 2 features, optimize these, and then the other are as good as it gets. A well-established compromise with existing technology is the following. It's a sequence from left to right. So the collision happens at the left. We get a shower of particles, or we get a muon, or we get an electron. The first we do is we track the charged particles. This can be done with comparatively little change to the energy of these particles. So we can measure, we will compute how much it's actually changed. But in the first assumption, to first order, it's not changed at all. So we measure the tracks of electrons and positrons, E plus E minus, B plus B minus, and kaons. We cannot measure the tracks of particles that have no charge, because these are ionization detectors and you rely on the charge. Then we put a high C material. We're going to discuss all these details. This is just the overview. Then we put the high C material with many protons in the way. That stops highly energetic photons and electrons. After that, we put, that's the electromagnetic calorimetry. Then we put hadronic calorimetry that stops the particles that are only that are predominantly strongly interacting. The kaons, for example, the neutrons, the protons, these are all examples of that. The charged one will leave a trace in the tracker, the neutral ones will not. Electromagnetic calorimetry and hadronic calorimetry, from the perspective of strong interactions, is the same. An electromagnetic calorimeter, even though it has a high C material, if a neutron comes along, it still sees the nucleus and will make a strong interaction. So the strong interaction happens in both electromagnetic and hadronic calorimetry. The electromagnetic interaction happens for the light charged particles and the photon only in the electromagnetic calorimetry. And then outside of this is a muon system, and we put it outside because we want to make it large so that we can measure the tracks of the muons with high accuracy, and we can measure the tracks of high accuracy because the muons are the one particle that go through all the detectors without depositing a lot of energy, but they do deposit some, so that we can actually track them. Muons make a nice ionization track across all subdetectors, particularly the tracking detector and the muon system, but the energy of those particles is not changed. Therefore, muons are the best, really the best final state particles in an event for precision measurements, for identifying the process, and so on and so on. Neutrinos are lost for practical purposes. We need to do this. Otherwise, we need to consider the transverse momentum balance. Now, there are two basic ways how a flux of particles reacts with the detector material. Remember, we have now can think of our signal as a bunch of particles that formed in a jet, or otherwise, two things can happen. Either a particle can be consumed by a single reaction, so it disappears. This is called absorption. Absorption means that you lose the particle, you completely use the particle in the first interactions. Low energetic photons therefore have a number density that falls exponentially. You can easily compute dn over dx. The loss of photons is proportional to the number of photons, which means the solution, I don't even write it down, the solution to this differential equation is an exponential falling distribution. That's one way to lose a particle in a single reaction. The other way to lose a particle is by energy loss through matter that's more or less constant with respect to energy. This is true for example, for heavy charged particles. This results in a limited area with a strong drop in intensity. The intensity of photons follows an exponential law as long as only as long as absorption is the dominant process. That's important. The energy loss of heavy charged particles at lowish energies follows a strong drop in intensity at the given distance inside the detector. The picture here shows alpha particles. The picture is very old, 100 years, almost. It's an alpha source on a photosensitive plate, and you see individually, you can see this with extreme resolution. You can see the individual alpha particles traveling through the material. They are created with the exact same energy, except this guy here, which came from an excited state. So they are created with the same energy. They lose their energy accordingly, but in a very similar fashion until they are stopped, all of them roughly at the same time, and then the intensity drops. This principle can be used to cure cancer, because with just the right energy, you can shoot highly energetic protons and have them deposit, or not only protons, also heavy ions, and have them deposit most of the energy deep inside, for example, the human body, when it's very hard, where it's very hard to do an operation, for example. So these are the two ways particles and rays can be absorbed. Now, maybe we do the math next time. It's 3. We've worked a lot. It's better to do it next time. The discussion that I will, for 2 minutes, I will walk you through what we will do next time in a little bit more organized fashion. We will consider a thin detector volume with a certain density of particles, and we will compute the cross-section from the ratio of rates that undergo an interaction to the rates of incident particles. That will give us a simple formula of the cross-section. So in a fixed target experiment, we only need to know the thickness of the detector and the incident and the final rate to compute the cross-section. We will then relate this to what happens in the thick volume of the detector and derive Beer-Lambert's law. You can already see, I believe, that these are very simple calculations, and I don't think, I mean, I will just draw them here on the slide. And then we will look at interactions of charged particles with matter. The big topic of next time is the Bethe-Bloch equation. This is the last calculation that we are doing in the whole lecture, okay? It will take 10 minutes. It's the last one, I think. The Bethe-Bloch equation is given, the Bethe-Bloch prediction is given here. It tells us about the ionization yield of heavy charged particles in practically any detector material. Bethe-Bloch equation rules detector physics. Whenever we have ionization, and that's the most important detection principle, whenever we have ionization, we need to consider the Bethe-Bloch equation, except in special cases. And we will talk about how the energy loss behaves as a function of the velocity, and then increases again if the momentum, if we are in the ultra-relativistic regime, that there's a minimum, and that in fact all these features are simple functions of the material properties of the detector. Good. That was a brief outlook. And it's 3. I think we've worked enough for today. And therefore I stop the recording.